Okay. Welcome everyone to the Thursday of bootcamp. Today we are going to be kind of having two tutorials, one in the morning, right now, by Han, and one in the afternoon. They're both about incentives and data sharing in collaborative learning. And we also have a lecture by Katrina in the later afternoon. So let me start by introducing Han. I've known Han for a number of years, since she was a first-year PhD student, I believe. Now she is an esteemed assistant professor at the University of Maryland. She started this year. Before that, she got her PhD at TTIC by Dalrymple Blum and did a postdoc at Harvard. Han broadly works on theory of machine learning, and some of the really cool things about her work is that she thinks about kind of what is the right modeling and foundations for ML if I actually care about interactions and data coming from different sources and people wanting their own thing out of their own data. So we are really happy to have her give this tutorial. This is a tutorial, meaning that you should feel free to ask lots of questions, and we'll go from now to 11:30, but the more interactive, I'm sure, the better. Okay, well, thank you.
All right, thank you, Nico, for the introduction. By the way, I just want to ask, is it okay for me to have like 10-minute break in between?
Yes.
Okay, yeah, because I think 2 hours is a little bit too long.
Yeah, it's good for the audience too, so if you want to, you tell us whenever you
Okay, great. Okay, so this tutorial will be about incentives for data sharing. So as you are here, so I think you know that collaborative learning enables large numbers of agents to share their data and collaboratively accomplish their learning goals. But in practice, data is costly to produce, but free to replicate. So agents will have cost for data sharing. Like the cost for data set curation, it's already hard. There is already a cost for collecting data. And they also, once they share the data, they will have to face the risk of privacy and security. So this creates a barrier for agents to share their data. And because of this, if they have a chance, agents will free ride on all those data. So for example, if we collect data to train a classifier to determining if a person has heart disease or not based on a person's age, and then consider we have two agents associated with two distributions, like say two hospitals, and hospital 1 has more younger patients and hospital 2 has more older patients. And for both hospitals, they want to obtain a model with at least 90% of accuracy. And so we, as a learning protocol, we request the data from both hospitals and then train a model. So this model is 99% accurate for the red hospital and 90% accurate for the blue one. And then, because when we get close to this threshold, the accuracy of the model for the red hospital is always better than the blue hospital. So when the data provided by the blue one is sufficient, the red hospital will free ride, meaning reducing the number of data they want to share, or even just contribute nothing. So this mode, yeah.
When you reported accuracy, was it the accuracy on the joint population, or was it the accuracy?
Everyone only care about the accuracy under their own distribution.
Patients, okay.
Yes, so everyone only care about their own local data distribution.
Okay.
Yeah. So this model is the central question of this tutorial. That is, how to incentivize agents to share more high-quality data. So the two main questions is about incentivizing and high quality. So for this part 1 of the tutorial, which means the tutorial this morning, I will talk about mechanism design for data sharing so that we can incentivize agents to share data. And for how to measure the quality of data is about data valuation, and Praneeth will talk about this in the afternoon. Okay, so let's talk about the model of data sharing a bit more formally. There are K agents, and every agent is associated with a data source. So their data sources can be different. There is a strategy space denoted by A. And every agent, they will choose a strategy, A sub I, in the strategy space, which determines a data set Si to share. The learning protocol will aggregate the data and then train a model using the pool data, and then share the model with everyone. Then every agent will receive a utility, we denote it by U sub I, which has two parts: the quality of the model they received, and the cost for data sharing. Yeah, and so notice that because everyone has a different data source, so the quality, even for the same model, the quality for a different agent can be different. It depends on the data source. And we assume that the agents are rational, so they will choose strategies that maximize their utilities. And so, yeah.
Look at the differential quality, meaning that if you were to only use your data, there's a baseline quality that you get, but now that you're getting this H hat, you hopefully will get better quality. So it's that delta between the two that matters minus the cost of sharing, or is the quality just like the quality of H hat?
The quality. So if you consider quality just as the accuracy of the model, and if you only use your own data, then you can measure the you know that you share 100 data points and you have accuracy of the model trained based on 100 data points. But if you pull the data, you have a higher accuracy. So that's come to the quality part. Okay. And so now let's consider. So still, this is a general. Still a little bit abstract model. So let's consider some more concrete and simpler case where agents only try to manipulate their contribution level. So in this case, every agent is associated with a data distribution denoted by D sub I. And the strategy space are just integers. So every agent, when they decide what data to share, they will choose a contribution level, which is sample size, M sub I, and then they samples their data set which are ID samples from their data distribution of size Mi. And then, because all the data points are ID samples, so for every data point, it will have the unit cost. So we can write the cost function of sharing Mi data points as a linear function of Mi. So the cost is written as like C times Mi for some constant C. And yeah, so this is a simplified setting. And in most of the tutorial this morning, we will focus on the simplified setting. That is, the agent won't fabricate data. They will only manipulate their contribution level. Okay, so we have the data sharing model. And what is the ideal strategy we want to implement? Like, how do we want agents to share their data? So a strategy profile is desirable if it satisfies the following properties. First, stable. We model stable by equilibrium. That is, at this strategy profile, A star, no agent want to deviate unilaterally. That is to say, for any agent, if they are given A star, they don't want to switch from A star sub I to another strategy because changing their strategy from A star sub I to another strategy AI won't increase their utility. So a benefit of a stable strategy is that if the learning protocol recommend a stable strategy, A star, then there is no reason for the agent to deviate. So they will follow A star. So we can we know what's going to happen if we know that they will follow A star. So we have a good control of this data sharing process. So this really matters because this can help to make the collaboration system stable. Still go back to this example. If the learning protocol only asks the rat hospital to contribute all the data, then the model is good, is overly good for the rat hospital. So the rat hospital have incentive to reduce their contribution and still have their objective achieved. But then the model is bad for the blue hospital. So as a learning protocol, if we didn't request a stable, strategy, a stable contribution level, then there are some participants, some agents, they might deviate, and then we have no control over the final guarantee.
So can I ask a quick question about the model? So when I decrease my contribution level, does that reweight the distribution that we train on, or do you how do you weight the contributions of the various parties? So if I am contributing 1/10 of my data versus all of my data, does my weight in the training data go down?
I think they just decide the exact size of the exact number of data points they contribute. So I think it changes.
I think they're both legitimate models. I'm just wondering if one of them's more interesting, or which one should I be keeping in mind? For
so are you saying that if they reduce their contribution, does it change my algorithm for training the model?
Yeah, so when we train the overall model, it's training on some distribution that is generated by the contributions of all the players, and should I think of that as having been sort of reweighted to sort of counteract lower rates of contribution, or should I think of it at?
Yeah, I think I will just I don't do the reweighting, so maybe I just train. I still just aggregate the data and just train training ERM over the data, and I don't do the reweighting.
It seems like maybe you're making a realizability assumption so far, which wouldn't matter if you rebate or not. You're just it's like a consistency or.
I
guess once you move beyond kind of realizability and consistency, that becomes a pretty fundamental question.
I think so far just consider using it doesn't change the algorithm. So yeah.
So I guess the equilibria you flashed on the screen a few slides ago looked like a Nash, and so I was wondering, does it make sense to think about things like correlated or coarse correlated equilibria in this setting as well?
I think actually it's more like I think it's more like I think later when we get into something, I think it's more. I think it's actually correlated equilibrium. Yeah. I think it depends. So I think so far, because this is still abstract, so it's kind of more abstract. That doesn't really say it's a natural or correlated. But I think later, when we get into some detailed model, I think it can be correlated equilibrium. All right. Yeah. So. So equilibrium really matter because when we only ask for contribution, stable contribution, then equilibrium, then we can keep the collaboration stable. And a state-of-the-art, commonly used federated learning algorithms might not be at equilibrium. So so in this paper we did some experiments. And to understand these experiments, if we just look at the result in this blue box, it's just saying that if we run federated averaging, and then we randomly pick one of the agents and reduce their contribution level to just 25% of their current level, then with probably 94%, the agent is still satisfied. That is to say, if we run federated averaging, 94% of the agent have incentive to deviate, has incentive to reduce their contribution to just 25% of the current level. As you say, if we just do around Federated averaging and request everybody to share the same amount of data, it is not stable. So far we have talked about like equilibrium as a very as a reasonable concept to model the stability. And of course, before we move on, we need to make sure that they exist. Otherwise, it doesn't make any sense to talk about equilibrium. And in general, they exist under some mild assumptions about the utilities.
So far, we are assuming everyone sees everyone's actions, everyone's like the impact of the action on the final model that they get, and they see everything. Because in this experiment, like in most settings, I won't be able to run the counterfactual. That if I leave, what happens?
Yeah. So I think it. So it depends on, like, this information might be given by the learning protocol. So the learning protocol can give the information about, like, what is their recommendation for contribution. And so if the agent assumes that everyone else will follow the recommendation, then they may also follow the recommendation. So it's based conditional on the recommendation of actions for other agents given by the platform.
Relatedly, are we going to get to talk about sort of dynamics of these kinds of systems? I can imagine an online sort of process where we would, discover and create the model over time and sort of modulate our rates of contribution and settle at rates of contribution, which could be super interesting. Is that a direction that's been explored?
That is not the same, because I think we still want the platform to play the role. So we don't want like agent to evolve over time and finally convert to some stable status. That is not what we want. We just want the platform find the stable collaboration and just publish it and ask everyone to follow. And so we don't have to do this in multiple rounds.
But that has been explored.
Okay, cool. I'd like to get references. Thanks.
Okay, so get back to the desired property of strategy. And beyond stability, another important property is efficiency. So we need some quantity to measure the efficiency of a collaboration. So for example, we can use social cost, which is a total amount of data, collected by all the agents. And or we could define, we could use social welfare, which is a total utility received by all agents. And by picking one metric, we can measure the efficiency of a collaboration. That is, the social cost or the social welfare at A star is close to that of the optimal collaboration. If this is the case, then we say the collaboration is efficient. And a third property that we want this collaboration to satisfy is individual rationality. That is, for every agent can benefit from the collaboration. So that is to say, the utility of agent I at this strategy profile is greater than the utility when they learning on their own. And usually it's easy to satisfy this individual rationality. So we mainly focus on the stability and efficiency. And usually there is a tension between the stability and efficiency because stability comes at a price. Yeah, so indeed, okay, so when we get back to, when we get out to the later, like some concrete models, we will see that equilibrium might not be efficient all the time. And in this case, we want to do some mechanism design to improve the efficiency by designing rules that aligns agents' incentives with a desired objective. So what the platform or the learning protocol can do is they may have more information about this collaboration than every individual agent. So they can share some additional information with agents, and they can specifically design the information they want to share. Or they can give some rewards to the agents after receive their data. Like the rewards can be monetary, or if an agent contributes more high-quality data, they can also receive more high-quality data. So this reward can also be in the form of data set. And by doing this, we can change the structure of the utility. Okay, So this is a basic the modeling and what we want to do in this to incentivize agent for data sharing. And the works in this area are very ad hoc. So usually different works consider different models, and they model strategic agents in different ways, and they also consider various different mechanisms to incentivize for data sharing. So in the following of this tutorial, I will just pick 3 papers like with different models and using different mechanism design approaches. So I think this 3 paper might have a relatively good cover of the works in this area. So the first one will be about using monetary payment to incentivize agents in the collaborative pack learning setting. And the second one will be like doing information design in a linear structured model. And in the third paper, I'm going to talk about a work on like they just want to collaboratively do normal mean estimation, and they will give like higher quality data, more high quality data to agents who share more high quality data. And for the first 2 papers, there's no fabrication of data. So they only decide their contribution level, and they won't like kind of like they only decide the contribution level and then sample truthfully report the data. And for the third paper, they allow fabrication of the data. I think we can have a 10-minute break maybe after the first paper. Okay. So consider collaborative pack learning. I don't know, can I assume everyone knows what pack learning is in this room? Okay, good. Yeah, so we just consider binary classification. And there are k agents. Every agent I has a distribution d sub I. We assume that all data are labeled by the same function h star, so that the data distribution d sub I can be written as a form of u sub I times h star of ui. Well, ui is a marginal distribution of agent I. So such similarity assumptions are necessary for benefit of collaboration, because if like there are 2 agents, but their labels are totally flipped, and there is no reason for them to collaborate to train a model together. And agent I will decide their contribution level mi, and then draws mi ID samples from their data distribution. The learning protocol will train the model using empirical risk minimizer over the pool data, and then share the model with all agents. So basically, they just look at the 0-1 loss over the pool data, and then return a hypothesis in the hypothesis class with a minimum empirical loss. And we assume realizability. That is, given a hypothesis class, this h star belongs to the h. And for every agent, their goal is to achieve a pack learning objective while minimizing their contribution level. So, for pack learning objective, say given epsilon and delta, they want the return. So they just want to make sure that with probability at least 1 over delta over all the over this data sampling process, the error of the return model is smaller than epsilon with probably at least 1 minus delta. And then we need to model the utility function of agents. So the agent's strategy space is contribution level, or saying their sample size. And based on their objective, achieving a pack learning objective with minimum contribution level, we can write their utility as the indicator function of their pack learning objective is satisfied minus their data curation cost, which is c times mi, for some small c. So originally they should minimize mi such that their pack learning objective is satisfied. So this can be written as this format of utility function by using some very small c. But this utility function doesn't work because this utility function depends on the on the distribution, so this is a function of dj, d sub j for all j. That is to say, this utility function depends on the label data distribution of all agents. And they don't know this, so no agents know this information, because if they know it, they even know the label function of, they even know the labeling function, and they know everything, so there is no point of training. So we need to relax this utility function. And one approach adopted by a lot of work is using some distribution-independent approximation. That is, although this error depends on like all the distributions by all the agents, but we can approximate by 1 over the square root of the sum of the data points shared by agents. By using the uniform convergence, the results in learning theory. But the problem is, using this kind of approximation, it's just weigh the data shared by others as the same as the data contributed by the agent themselves. So this is not true for the heterogeneous data collectors. So if we just consider like 2 agents share their handwritten digits, and then if we just change the fraction of each agent, the accuracy will actually change. So this is not true for the heterogeneous agents. And another approach is by worst-case approximation. So we can consider some application scenarios such that the marginal distributions are not that sensitive, but the labels are very expensive. And then we can request all agents to publish their marginal data distributions, but not their labels. And then the agents can aim to guarantee their the worst case error, while the worst case is taken over the option of the labeling function. So in this case, we can rewrite the learning objective by replacing this d sub I by the marginal distribution times which are labeled by h, and in the worst case of h. So we just want to guarantee that no matter what the labeling function is, the packed learning objective is guaranteed. So we just replace the true learning objective with the worst case objective. All right. So now the utility for the agent I is the indicator function of like worst case learning objective is satisfied minus the cost. Yeah.
I was just thinking, why isn't the utility defined as something like the error or the expected error minus?
Oh, you can also do that.
And, okay.
Yeah. I think this is just one example. So usually, I think this also works if we consider expected error.
But we want a deterministic thing to go there, and that's why, and we want the high probability guarantee, so that's why.
Yeah, I think we just want. I think this paper really requires its indicator function of some error guarantee to be satisfied. So that is a structure that is required for this. But it doesn't matter if it is packed learning objective or expected accuracy objective.
Things would be equivalent, you're saying?
I think all the things will still apply. Yeah. Okay. So in this case, equilibria still exist, but they might not be efficient. Any equilibrium might require much more data points than the optimal collaboration. So here's an example. We consider like the hypothesis class are just singletons. And then there are 2 agents. So agent 1 just pick 1 over 2 epsilon points and put 2 epsilon on each of these points. And for agent 2, it's put problem mass 1 over epsilon over 2 largely on a point that everybody knows that is certainly is negative, and epsilon over 2 on one of these points. And in this simple example, in any equilibrium, agent 2 has no incentive to contribute anything because every hypothesis has error below epsilon over 2 for agent 2. But for agent 1, she has to collect all the data points here, because when the true hypothesis is H0, which means every point in, which means for the points in the distribution support of agent 1, the hypothesis class are all singletons and all negative. And when the true labeling function is all negative, and for agent 1, to tell if it is really all negative, they have to collect all the points, x1, x2, up to x1/2 epsilon. So just using coupon collector, they have to, they need like log 1/epsilon divided by epsilon samples. But in the optimal collaboration, we only need one, because if we could sample this x0, then we can guarantee that when the target function is this one, we don't have to collect x1 to x1/2 epsilon. So in the optimal collaboration, we only need 1/epsilon samples from each of these two agents. So equilibrium can require log 1/epsilon times more samples than the optimal collaboration. So when epsilon goes to 0, the gap can be arbitrarily large. So equilibrium can be very inefficient. So then we consider, okay, so we really want to have something efficient, because
can you just go back to the previous slide? Why does agent 2 not have no incentive to contribute anything?
Oh, because they only care about if they can obtain a classifier with error below epsilon. But since this point is certain, because all hypotheses will label this as negative. And for this point, although it's uncertain, but the problem is only epsilon/2, so every hypothesis can achieve error smaller than epsilon for agent 2. So agent 2 doesn't need to collect any data points.
Okay.
Yeah, okay. So equilibrium can be inefficient. And, but we want the collaboration to be efficient. A natural fix is to appoint a central planner, such as a regulator or platform operator, who can dictate how many label examples for each agent contributes. So what we can do is the central coordinator will publish a payment rule, and then ask agents to report their marginal data distribution. And then the agent will report, but maybe they can tell the truth, or they don't. And after we receive the reported marginal data distribution, the central platform, can compute a contribution solution and then enforce it. And then the agents, so the rule for them to join the collaboration is they have to follow the contribution decided by the platform. So they will share the data of at the level of M star. And then after aggregating the data, the platform will train a model and then share the model and pay the agents. So with this central coordination, it formulates a new game. Formula the new game. So the agent strategy space is not about contribution level anymore. It's about their reports of their marginal data distributions, because now the only thing they can play with is they might misreport their marginal data distribution, so that maybe they can benefit, try to manipulate the system. So the utility is still indicator function of whether their objective is satisfied minus their cost. But now this cost is a function of their reports. And in this new game, there are two questions. The first thing is about computation, a computational issue. That is, given these marginal distributions, how to compute a contribution level M. Ideally, we want to compute the optimal solution and then enforce everyone to contribute at the optimal level. So that is the most efficient thing for us to do. And the second question is how to incentivize agents to report their marginal distribution truthfully via payments. So the first question, about computing the optimal solution. So the optimal solution can be calculated by solving this constraint optimization problem, that is, minimize the total number of data points such that the worst case pack learning objective is satisfied for every agent. And so basically we just want to look at, so for every edge, when it is a true labeling function, we just want to look at the discriminant region between H and all the other hypotheses. And so agent I's constraint is satisfied if with high probability, we can obtain points from the discriminant region between H and any other bad H prime. So if we have samples from the discriminant region between H and H prime, we won't return H prime. So this problem actually can be reduced to the set cover problem. So we can show that solving this optimization problem exactly is at least NP hard because we just want to cover the disagreement region for every hypothesis, and this can be reduced to the set cover problem. But this problem can be solved approximately easily. We can just we can use linear programming and to solve it. So I think how to solve it doesn't matter that much, but I think what's important here is that solving it exactly is very hard, and it's computationally hard. So we shouldn't expect to solve this problem exactly. But obtaining an approximate solution is easy. So then we want to talk about mechanism design. That is how to incentivize agents to tell their to report their distribution truthfully, given that we only have approximate algorithm to solve that optimization problem. So a payment mechanism is truthful if it can incentivize agents to report their distribution truthfully. So they won't benefit from misreporting. And why the calculating the solution, optimal solution exactly versus calculating it approximately matters is that if we can calculate exactly, we can just apply the classical VCG mechanism to design the payment. So what is a VCG mechanism? Suppose we can solve this optimal solution. And then we can pay each agent I by the summation of the utility for all the other agents at this optimal solution, plus some irrelevant thing. Just ignore this part. And so basically, you just pay everyone else, pay agent I by the summation of the utility of everyone else at the optimal solution, which is equal to k minus 1 minus the cost of other agents. And then by paying agent I this amount, then what the agent I will finally get is their utility plus their payment. That is the indicator function of their objective being satisfied plus some constant minus the total cost by everyone, including agent I themselves. So if they misreport, then either agent I's objective is unsatisfied, or she will be asking for more data because we have exact optimal solution. So once they report truthfully, this is already the optimal, is the minimum sum of the total cost for agent is already minimized when they report truthfully. So by applying VCG, we can guarantee that every agent will report truthfully. But we cannot apply VCG here because they really require exact optimal solution, and calculating the exact optimal solution is hard. So an alternative payment mechanism is pretty trivial. Just pay exactly what you contribute. So they have a cost for sharing MI data points. They have a cost of C times MI, and we just pay them the same amount of their cost. And so their cost for data sharing and the payment will cancel. And so they just don't care about how much data point they have to share. So this payment mechanism is very trivial, and but we can show that if we only have access to, if the payment mechanism is also have some computational issue, then this is the only truthful mechanism we could have. So what do I mean by that? The payment mechanism also have computational issue, computational limitations. That is, usually the payment mechanism is a mapping from the report to a vector of payments. But it's hard to design some payment mechanism as a function of the marginal data distribution. So if we just consider a restrictive class of payment mechanism, that is, it is only a function of the approximate contribution level. Then for this category of a payment mechanism, which only depends on the contribution level calculated by themselves, then this is the only truthful mechanism they can do. Just pay exactly what they get, pay exactly what the agent contribute. So, but why it matters? We have a mechanism. So why do we still want to argue this is the only mechanism we could come up with? Because this mechanism doesn't satisfy some other desirable properties that we usually want. So for a payment mechanism, we want this payment mechanism to satisfy weekly budget balance. That is, its agents pay the coordinator. Instead, the coordinator pays the agents. Because it's kind of weird that the agent join the collaboration, and then they can get money from the platform. So maybe we want the agents to pay the platform. Or even a better property, a more desirable property is a strongly budget balance. That is, the total payments made by the agent is exactly 0. So all the payment will only redistributed among the agents themselves, so that we don't have to the center just redistributed the money, but they don't have to provide any monetary payments. But the trivial mechanism I just mentioned doesn't satisfy these properties. But it seems that if we have computational limitations, there is just no way for us to also achieve these desirable properties. Yeah. Okay, I think that is a part for the payment mechanism for data sharing. Yeah.
So in the previous model, you're assuming there can be arbitrary misreporting of the data distribution from the agent.
Yes.
Is there a way to constrain that to sort of get around this?
But how can you restrict them?
Because if I'm asking agents to report, let's say, some health record data, I mean, they can only report health record data. They can't report something else. If they're reporting a chest X-ray, it'll still be a chest X-ray. It's very hard to curate a distribution of chest X-rays which is biased to have a particular downstream effect on a machine learning model. Mm-hmm. So there's it's natural to me that there's some constraint you want to have on the misreporting.
Yeah, I'm not sure because there could be some constraint, but here we just but this still works if you have constraint, right? Because this can guarantee that the best thing you can do is just to report truthfully.
So your point is that there could be other mechanisms as well, but
yeah, maybe if you model this constraint explicitly, and then maybe there is some other.
Yeah, I mean, here you're mentioning that there's somehow these nice properties not being satisfied.
Yeah. Yeah, that could be true. Yeah, I think in this paper they have some budget balanced mechanism, but in this paper they consider this they use this distribution independent approximation instead, so they cannot consider the heterogeneous setting.
Yeah, I think it's the homogeneous setting in this.
Yeah, it is still considered homogeneous setting. Okay. Do you think it's good to take 10 minutes break right now?
Okay, that sounds good. So it's 10:18. I guess let's be back at 10:28, and then we'll have 1 more hour. Okay.
That's all. Did you get your last one?
or chat?
Yeah, I arrived. I think I arrived at like 4 a.m. So 3:30 a.m.
I left this building at 4.
I saw your messages. I think I replied to you after when you were saying.
I was like,
Did you drive?